Hi everyone. So today I want to start talking about similar matrices, and similar matrices are nifty for a bunch of reasons, but our main goal is really to talk about diagonalizability. So first I just want to introduce this more general notion, and then we'll start in the next video to see what it's like to be diagonalizable and how to diagonalize a matrix. Two matrices are similar if they're related to each other in a special way by another matrix. All the matrices are assumed to be square and of the same size. So this says that these two matrices are similar if you can find a matrix M so that M inverse times A times M is equal to B. Now just using basic linear algebra, we can rewrite this as AM equals MB, right? Taking M and multiplying on both sides. And multiplying on the right by M inverse, we can get this. So these are all three equivalent ways of saying that two matrices A and B are similar. So here's an example. So these two matrices, A and B, are similar. And you'll notice that I've used this notation to denote similarity. So we can see this if we can find an M so that the property holds in one of any of these three forms. So here's an M that'll work. And now to check to see that this witnesses that A and B are similar, we just need to carry out the multiplications, right? So we're going to take M inverse times A times M and see if we get B. So here's the product we need to calculate. I'll do it kind of step by step. So now we have 20, 26, 14, 18 times still that matrix M. So these two matrices are indeed similar, and that fact is witnessed by this matrix M. Now similar matrices have some really nice properties that are not too hard to prove. So for example, two matrices that are similar have the same determinant, and that comes from the fact that the determinant of the product is the product of the determinants. So the determinant of B is equal to the determinant of M inverse times the determinant of A times the determinant of M. And that's equal to, since the determinant of the inverse of a matrix is 1 over the determinant of the matrix itself, we get this. And since these are all scalars, these determinants cancel out, and we're just left with the determinant of A. Now I won't go through the proofs of these other properties that I'm going to write down, but you can check them. One says that A is invertible if and only if B is invertible. These two matrices have the same rank. And last, A and B will have the same spectrum. That just means they have the same set of eigenvalues. So it may not be obvious at first why we should care about similar matrices, but here's one example of why we should. So let's suppose that A is similar to B. So A is equal to some M times B times M inverse. And let's further suppose that we've been able to find a B that A is similar to that is a diagonal matrix. Now that is a super handy thing to have if you're trying to compute powers of A. So if we want to compute, say, A to the 10th, that's going to be exhausting and computationally intensive. However, if we're able to find a similar matrix that is a diagonal matrix, then computing A to the 10th is actually pretty easy. Because if we write out those powers of A using the decomposition into M, B, M inverse, this is what happens. And you can see that all along this big product where we multiply M, B, M inverse by itself over and over again 10 times, we have all of these instances of M inverse being next to an M, and so they cancel each other out. And what we're left with is just M times B times itself 10 times M inverse. Now it looks like we've reduced the problem of computing the 10th power of an arbitrary matrix into computing the 10th power of another arbitrary matrix, but if B is a diagonal matrix, it's easy to compute powers. Because if it's a diagonal matrix, then when we compute a power of B, we're just getting another diagonal matrix with the entries raised to that same power. So B to the K would be equal to D1 to the K, D2 to the K, all the way down to dn to the k with zeros everywhere else. So now we have this really easy power that we can compute. B to the 10th is just going to be whatever the diagonal entries are raised to the 10th power. And then there are only 2 matrix products to compute instead of the 9 that we'd have to compute A to the 10th. So when we can find a diagonal matrix that is similar to a matrix that we're interested in, that's called a diagonalization of the matrix A. And in the next video, we'll see how to do that.